Hi everyone. For our last lesson, we are going to look at how we can analyze networks that are larger than what we can visualize, as we've been doing earlier. In this session, we're going to both look at how we can use statistics for those networks and eventually look at the ways in which we can visualize them by exporting them from R and using a program that is a little easier to work with and I think does a little better job of allowing us to create diagrams that you can get some subjective sense of a network from when you move above a very small set of nodes. For this project, we're going to use the country music data that I have collected. I did this by scraping several different websites, and in the end I have a data set that has about 60,000 songs from 1950, well, the late 1950s to 2019. It has data like artists' names, the titles of the song, the album, the year they're from, and particularly of interest for us, they have all the other artists that are mentioned within a song. So, if there's somebody driving down a dirt road who's singing about listening to Johnny Cash, that shows up as name of the artist, Johnny Cash as a referenced artist. So we're going to make some graphs from these references. So our first step, as always, is to import the data. So go download the data and put it in a folder where you know where it is. I'm up in the options going to set my working directory like this, and I'm going to run that. Why did it import it already? I'm not sure, but it did. Final Countrywide is the name of the CSV. So we should be good. Everything should be in. Oh no. There we go. I guess it didn't import before. It just randomly showed me all of the specifications. So here it is. We see DX up here. Like I said, there's 45 variables. Names, lyrics, the source. And most of these, as you can see, variables 1 through 33, most of them are blank. What these are the references. First reference, second reference, third reference. 33 is the greatest number of references in the data set, so that's the number of variables there are. Let's move on. Now we have to think which of these we need, because certainly all of these aren't network data. What do we want to turn it into? An edge list or an adjacency matrix? As usual, when we're working with survey-style data, it's easier to turn it into an edge list. So how are we going to do that? We can think of a couple steps here. But the important thing that we need to think about as we do so is that I'm also interested in making separate graphs by period. I want one from 1980 and before, one from 1981 to 2000, and one from 2001 onward. So I need to do a couple of data tasks. I first need to, well, I can do either one in either order. I need to split them into different eras, and I also need to end up with something that looks like an edge list. So how do I do that? Well, I decided to turn it into an edge list first and then split by period. I'm going to use this package called Pivot Longer, which is from dplyr, or at least from the tidyverse. It's not from dplyr. I think it's from tidyr in the package, but part of the whole same universe. And for that, you say what data frame you're working in, and then the list of variables that you want to pivot longer, to essentially go from wide form to long. Now, remember when we used reshape2 and melt? We gave it a vector of ID variables. This, we give it the variables that are essentially not the ID variables, the ones we want to spread out. I think that's a little more intuitive. Really, I just choose whichever one I think will be easier given the data structure and the situation. Here, all of the things that I want to serve as the variables that are made long are all together. So I use this. Now, Normally you wouldn't have to put as character here. The only reason I have to do that is because randomly in my data, the variable names are 1 to 33. So it immediately thinks I want something numbers 1 to 33. I tell it it's these characters. I look at this as the set of things I want, and I tell it make that longer. So I do it. Let's run just that line. Now, if I look at that, holy crap, we have 2,022,702 observations. Why is that? Because for each line of the original data set, it created 33 different lines in the long version. Now, I told you I think only one song in the whole 60,000 data set had 33 references. So most of those lines are going to be all the same, and then they get to the value over here, and it's going to be NA. So we can get rid of one of those. Oh, see, it takes us the whole way down here to find a single reference. We can deal with that pretty easily. We are going to we're going to filter our new data set, and say, is NA for the value equals false? We take those out, and we're left with a much more manageable 2,747 observation data set. A little easier than 2 million. Having transformed to long data, now we need to filter by year and then select only the columns that we want. We can do this. That ran more things than I expected once again. I don't know why that is, but it works for us, so nothing is really hurt by that. Let's look at our ran that whole chunk. Let's do it in order. Let's go back, run these selected lines, run this as a single line. We look, we see that we don't need the URL where I got this from, any of these things. We really just need the artist name and who was referenced in the value. So we go back here and say, let's select those two things. We run that. Still don't know. Now we can look here and we have a nice pre-1981 data frame of artists and the people that they referenced in their music. We can graph our data frame. If you wanted to, you could do as.matrix and then graph.edgelist. Works almost exactly the same. I choose to save a step here. We're going to treat these as directed because one person is singing about someone else, so it makes sense to us. And we call this graph G1. As R has precociously plotted, you can see that when I plot it, even in this graph, which is going to be by far the smallest of the eras that we do, I just can't get that much information from it. So what I want to do is go and figure out how I can analyze a graph that I can't really see what's going on. And my first option is to do it statistically. To start this, we want to make a data set from the different statistics we can calculate from our network. To start out, I usually just create a vector with the name, essentially the names from our vertices. I selected lines. I guess even though it showed me this, it didn't actually run it. Let's do that. Let's do this. And now let's get down here and see if this works. We now have an object G1, so it should. Run, unselect lines. I now have a name vector. Since this is in the vertex order, all the vertex properties that we calculate, all the vertex statistics, are going to be in the exact same order. I calculate in degree, out degree, alpha centrality, which is our weighted monocyte centrality measure, and betweenness. I leave this at the default for alpha, and we run it. So now I have a bunch of different vectors. I'm going to take all of these, and I'm going to put them into a new data frame. Could we have created a data frame at the beginning and then written each one in as we go along? Yeah, sure, but this is just as easy. So I'm going to say data frame. I want this name, in degree, out degree, monocyte centrality, betweenness, and I'm going to tell it strings as factors equals false, so it doesn't treat my names as strings. Doesn't treat my names as factors. We run it, and now we have a nice data set that we can analyze. This one's pretty easy. There's actually only 70 observations. It'll get bigger for the next ones. So, here we go. Let's find out who's at the top of in degree. It seems like Hank Williams receives the most nominations, followed by Willie Nelson. How about out degree, sending the most nominations? It's Hank Williams Jr., followed by Johnny Cash, followed by David Allan Coe. So, Hank Williams Jr. sent the most, Hank Williams, the father, received the most. Maybe there's some little family inside stuff going on there. Let's look at centrality. What would we expect? People who are going to be highly central are those who are not just getting a lot of nominations, but receiving a lot from central individuals. Here we go. So interesting, Willie Nelson jumps Hank Williams, and Jimmy Rogers, who wasn't even on our in degree measure. Oh, never mind, he was fourth. Jumps to the top. How about betweenness? We told it's directed. And let's run. So Johnny Cash is actually really central by betweenness, as is Merle Haggard and Hank Williams Jr. These are the people who are connecting the graph because they're both sending and receiving some ties. You see a lot of the people who are just receiving ties, like Hank Williams. Hank Williams Sr. was actually dead before this data set starts, so he's obviously not going to be sending out a lot of ties. These people are both sending and receiving, and that's just going to make them so well connected in terms of betweenness. Another thing we can do is look at the way in which some groups are closer to others. We can look at clusters. There's a lot of different ways to look at clusters within a network, as we've talked about. My favorite algorithm is the random walk. So we're going to use this walk trap community algorithm, again from iGraph, and essentially what it does is it picks random nodes and then goes randomly along its connections and sees how quickly it overlaps and where it densely overlaps and where it doesn't. You can set walks at different lengths. This one is set at 4. We run this, and what we're interested in is this membership. We're going to see which groups it assigns different people to. So if we look at this, we can see that we get a bunch of different people assigned to 1 through 10 different clusters. It's going to assign everyone to a cluster. So some people will be more or less densely connected, and you can later go back and look, if you just looked at individual clusters, which of those individuals are most densely connected. But we could then use that. We could look at the graph and see if being a member of certain clusters has effects on different of the individual statistics. When we graph it, we could make those colors say different colors, and then we could potentially see macro patterns even if we can't see individual network connections. Now, as I mentioned before though, it's often pretty hard to visualize this size network, and as it gets bigger, and they get a lot bigger, it only gets worse. So what we're going to do is export it from R, which I don't think does a great job with this, and import it into Gephi. I think you're going to like Gephi, so let's get ready. First, we're going to make this as an edge list. Now, for the astute of you, you might think, wait a second, we already had an edge list. That's very true, but that's not always the case, and sometimes we have merged graphs, taken things in, put things out of graphs, and so it's sometimes nice to just create an edge list from the final graph that you're working with. To do that, we use as_edgelist, we name it something, we run it. Now, to export our data, we want to use write table. Write table works better than write.csv here because write.csv will ignore this call names equals false, and we don't want the first row of our data file being v1 and v2. Gephi doesn't know how to ignore that. So we're just going to say write table, which is the more general command, and we then will put a comma as our separator, which creates a comma separated values file, even if we're using the more general command. If you are noting that this jumped as the screencast goes on, that's because I didn't realize this until I got to Gephi and imported my file. So I went back, changed this to write table rather than write CSV, and I don't have a random connection between v1 and v2. So the first thing you're going to need to do is go get Gephi. To do that, I would just Google Gephi. Gephi.org is the site, that's gephi.org, and download free. So download that, click install. It's not a big program. It should be pretty easy. So once you've downloaded it, you want to open it up. Gephi looks like this. So now let's bring our data into Gephi. We go up and we click File, Import Spreadsheet. You want to go to wherever you saved it here. Mine's already there, but you might have to navigate to it and find the file that you just created. Mine is this one. So I click on it, and I'm going to check the separator as a comma, import it as an adjacency list. So if you try to import it as an edges table, it's not going to quite work right because you need to essentially have a specific column name for each of them, but adjacency list works with nothing. Next, time representations intervals, that seems fine. Finish. Parallel edges detected, that means multiple people are essentially nominating the same person. Hank Williams Jr. is probably nominating Hank Williams Sr. like 11 times a song. We're just not going to merge those. Sum, average, we'll try first. It doesn't really matter because we only care about one. We're not going to weight the edges right now. If you want to weight them, just merge them. Okay. So, it's not very exciting. Let's go look at our window and make sure we see our graph. Oh, there's something. Seems a little clearer. And the nice thing about Gephi is you can play around with stuff. We're going to choose a layout. I like Force Atlas too. Is it because it sounds dramatic? Maybe. Pause it. For zooming in and out, this is randomly difficult. You move in and out as in up and down. It's not the nice. And wherever the middle of your cursor is, that's where it tries to zoom to. So I mess this up all the time. You can get away from that by just going back here and clicking. Where do you click? Put us roughly in the middle. So here we are. Force Atlas 2, we can also change things. We can change the scaling. Let's say double the scaling. Run it. Now things are spread out a little more. You can try different algorithms. We can try repulsion strength, traction strength. Obviously, you can imagine what those do. And you can find something that works for you. So now that we're here, let's put it in the middle again. Let's zoom right to there. And let's play with some stuff. Let's put our labels on. To put our labels on, we click down here. Wow, those are a little big. Let's make them smaller. Now we have nice small labels. Let's make those a little bigger. We can change the arrow size like this. Change its color, I think. There we go. But you can actually change the color rather, since my color is just gray here. It didn't look like much. You can change a lot of things using these couple menus here. Color, size. When you're done, you're going to take a screenshot of your graph. So you just need to put it somewhere, take a high-res screenshot, and you'll be able to see things. As we know, it's kind of fun. If you click on one, you can see all its connections. So say we want to change the size of the nodes. We go up here, we go to nodes. You have color right there. Unique, this means we're going to tell it something. Ranking, we don't have, oh, we do have 3. You can also calculate a bunch more things over here. We could calculate, say, well, network diameter is not going to help us. If we're doing individual, let's run eigenvector centrality. Oh, there we go. So now let's scale them based on eigenvector centrality. It's up there. Let's go to size. Let's do it by ranking. Eigenvector centrality. Let's apply that. And now we see that people with high centrality are much larger in our graph. We could change the color, we can change text, we can do a lot of different things with this, and you can calculate them pretty easily through here. This Gephi isn't as good for analysis, but it's actually really good for visualization, and you can make a lot of reasonably good-looking big networks with this. One thing I like to do is I like to go over to my text labels and scale that by centrality, because that way, oops, well, that was too big on those. You can essentially get the people you don't care about out of the way for the nodes that you do. So that's Gephi. You can play around on it. As you can see, it's click and drag. So you can make a big network look reasonably discernible using this software. So if you would like to try that, you should try it on the 1980 to 2000 data and see if it's any different from the 1957 data that goes up to 1980. Good luck.